In this tutorial, we are going to evaluate x squared plus y squared dx minus 2xy dy along the closed curve C, where C is a semicircle in the first and second quadrant. And that semicircle has a radius of 2, and it is centered at the origin, and is defined by x squared plus y squared is equals to 4. So for us to evaluate that line integral, it is convenient to split the curve C into two parts, C1 and C2. So I'll call that part C1, the one that is defined by x squared plus y squared equals to 4. And the horizontal part there, I'll call it C2. And therefore, our integral along the closed curve C will be the integral of x squared plus y squared dx minus 2xy dy along the curve C1 plus the integral of x squared plus y squared dx minus 2xy dy along the curve C2. So now looking at curve C1 there, we see that it has a term which has x squared plus y squared. And in this case, it will be convenient to use polar coordinates, because they will make evaluation of the integral a bit easier. So if you are looking at that equation and compare with the equation of a circle centered at the origin, we have x squared plus y squared is equals to r squared. What we see when you compare those two, we see that our r, the radius there, is a 2. And when you are transforming to polar coordinates, we would have x is equals to r cosine theta. But we said our r is a 2, therefore we would have x is equals to 2 cosine theta. Our y is r sine theta, and we said our r is a 2, so our y will be 2 sine theta. We go on and differentiate x with respect to theta, and we get the derivative of x with respect to theta is minus 2 sine theta. Then differentiate y with respect to theta, and we get the derivative of y with respect to theta is equals to 2 cosine theta. So we have the derivatives there, and from those derivatives we can find dx in terms of theta and d theta. So from that equation, we get that our dx is minus 2 sine theta d theta. And from the second equation, we get that dy is equals to 2 cosine theta d theta. But you should recall that when we are measuring theta, we measure it from the positive x-axis in the counterclockwise direction. So what we have is we start at 0, going in the counterclockwise direction, and go up to pi, then come back to 2 pi there. So in our case, we are starting at the point 2 there. So that means the theta will be 0. And where we end the curve C1 there, the theta will be a pi. So what you are having there is theta is varying from 0 to pi. Now to evaluate our integral, the integral of x squared plus y squared dx minus 2xy dy along the curve C1. We said our limits, they are from 0 to pi. We can separate those parts that have dx and dy. So I can write it as the integral from 0 to pi of x squared plus y squared dx, then minus the integral from 0 to pi of 2xy with respect to y. And that is just using properties of integrals. But if you look at the equation that defines that curve, x squared plus y squared is equals to 4. In our integral there, we are having a part where we have x squared plus y squared. But from the defining equation, we are saying x squared plus y squared is equals to 4. So we can put that there into that integral. So we have a 4 there. And we also look at the dx. We say it is minus 2 sine theta d theta. And the dx, we'll put it there where we have the dx there. And that first integral will become the integral from 0 to pi of 4 multiplied by minus 2 sine theta d theta. Now we go on and look at the second one now, the integral which is 2xy dy. it is an x and y, but we have our x there is 2 cosine theta, our y is 2 sine theta. So we put that xy there in that integral where we have the x and y. And then we need to look at the dy there. It's 2 cosine theta d theta, and we'll put it into the integral there where we have the dy. Therefore, that integral will become the integral from 0 to pi of 2 cosine theta, 2 sine theta, 2 cosine theta d theta. And we can simplify that to the integral from 0 to pi of minus 8 sine theta d theta. And the second one is minus the integral from 0 to pi of 16 cosine squared theta sine theta d theta. So we are having the integral along the curve C1 there is on that part. Now let us evaluate those integrals. Start with the first one there, the integral of minus 8 sine theta with respect to theta from 0 to pi. The integral of sine theta is minus cosine theta. But you can start by factoring out the constant there. We have minus 8 multiplied by the integral from 0 to pi of sine theta d theta. But the integral of sine theta is minus cosine theta. So we have minus 8 multiplied by minus cosine theta from 0 to pi. When we substitute the limits there, we'll get and that value is a minus 16. So for the highlighted part there, we have that is minus 16. Now looking at that part there, we are now going to evaluate the integral from 0 to pi of 16 cosine squared theta sine theta d theta. And we can factor out the constant, the 16, and we have 16 multiplied by the integral from 0 to pi of cosine squared theta sine theta d theta. And to evaluate this integral, we can use a substitution. So we let u is equals to cosine theta, then differentiate u with respect to theta, and we get the derivative of u with respect to theta is equals to minus sine theta. And we can go on and make d theta the subject of the formula, and we get d theta is equals to minus du divided by sine theta. And when you substitute into the formula there, where we have cosine squared theta, it will become a u squared. Then where we have sine theta d theta there, what we would have is sine theta multiplying minus du sine theta, so it would be minus du. So we have 16 integral from 0 to pi, the u squared times minus du. And that will simplify to minus 16 multiplied by the integral from 0 to pi of u squared du. The integral of u squared is u cubed over 3. So we would have minus 16 multiplied by u cubed over 3. Then you put the limits 0 to pi. But when we started evaluating this integral, we used the substitution u is equals to cosine theta. So we can now substitute where we are having u there. We substitute the cosine theta, and we would have minus 16 cosine cubed theta divided by 3. Then put the limits 0 to pi. And when you put in those limits, we'll get that the integral is 32 divided by 3. So what you are having is for the integral, which is highlighted on the right there, and the value is minus 32 divided by 3. And minus 16 minus 32 divided by 3, it gives us minus 80 divided by 3. So what we are having there is the integral of x squared plus y squared dx minus 2xy dy along the curve C1 is minus 80 over 3. So we can now move on to the integral along curve C2. What you can see in the counterclockwise direction along C2, y is 0. Therefore our dy will be 0, and x is varying from minus 2 to 2. So to evaluate the integral of x squared plus y squared dx minus 2xy dy along the curve C2, we substitute the values that we are having there, and we have the integral from minus 2 to 2 of x squared plus 0 squared dx minus 2x times 0 times 0. And it will simplify to the integral from minus 2 to 2 of x squared dx. And the integral of x squared is x cubed over 3. And when you put the limits minus 2 to 2, we get 16 over 3. So what we are having there is the integral of x squared plus y squared dx minus 2xy dy along the curve C2 is 16 over 3. Now to evaluate the integral along the closed curve C, we have to add those two line integrals, and you get minus 80 over 3 plus 16 over 3. So that will give us the integral along the closed curve C. Minus 80 over 3 plus 16 over 3, it gives us minus 64 over 3. So what we are having is the integral of x squared plus y squared dx minus 2xy dy along the closed curve C is minus 64 over 3.